Skyworks' high-performance, leading-edge analog semiconductors are linking people, places, and things across a growing number of end markets, including aerospace and defense, the connected home, consumer electronics, infrastructure, medical, mobile devices, networking, smart energy, and wearables. Skyworks' ability to integrate multiple bands and frequencies on a single device means Skyworks sets the standard for technology in today's Internet of Things.
The Internet of Things, the connected devices, the connected home, world, automobile, these are all being enabled by small, fast, affordable devices that Skyworks produces. We're actually enabling much of the technology that you're going to see in the next decades.
Skyworks is a company that at its core enables the heart of mobile connectivity. And mobile connectivity could be your Wi-Fi router, a smartphone, navigation in your automobile, connected home, a vast number of devices that really embody what the internet is about today. We enable that. We enable it with powerful solutions, leading edge technology, with a focus on customers.
And Skyworks is able to produce a whole number of components that make the Internet of Things possible.
You probably use our product every day but have no idea who we are.
I said, do you have a cell phone? They said, yeah. I said, there's parts that my company makes that are in there.
That ability to connect to both people and things, I think, makes Skyworks in a very exciting place, and then our products and services that much more valuable within the social environment and also within the world of technology.
And my daughter, who is 4 years old, she knows where to tap on a Skype app on the mobile phone and talk to her grandmother thousands of miles away. And nothing can be more satisfying than seeing that happen.
Our people can see the actions and the work that they do and how it translates into the market and the impact that it makes on the world.
Skyworks wins over the competition by being fast to the market, and I think by listening much more intensely to what our customers want. We're trying to deliver always on time. We're trying to deliver a perfect quality product, and we strive to put ourselves in our customers' shoes and solve their issues. And to the extent that we can do that, our products will always win.
Hi, my name is Carlos Lares, and I will be co-presenting with Ryan Welch-Luttrell. The name of our presentation is Job Shop Characterization Lab. I work for a company called Skyworks Solutions. We have a little bit over 10,000 employees worldwide. This company is focused on solving wireless communication problems, and we have customers on many segments like aerospace, automotive, medical, military, to mention some. So I'm a business unit operations manager. I'm responsible for the areas of test, assembly, materials, and data engineering. And I work for a business unit called Diversify Analog Solutions. Part of our responsibility is to support design centers across the United States, Canada, and Ireland.
And my name is Ryan Welch-Luttrell. I'm a solutions engineer here at Simio. I've got about 10 years of experience with modeling with the software. And over my time here working with Simio, I've really been responsible with engaging with our customers to maximize the benefits of them using the software, which includes project support or just general technical support.
Just to give context of where the problem that we're trying to solve resides within Skyworks processes. Skyworks develops product in a phase approach, like probably any other company, and we use a process called product realization process. So within that process, there's two specific phases that we're going to be focused on. Those are phase 2 and phase 3, which some of the RF testing is happening. So the scope of the project is in this RF test process, and mainly on the Characterization Lab with this RF testing takes place. In order for us to being able to model the test lab, we need to consider 4 main aspects or characteristics. As you can imagine, in a test lab, you need to have test setups, and those test setups, they are very versatile. You can change over those setups within minutes, so they can test different characteristics from the parts that we test. Also, we need to model the test plans. Test plans can be as simple or as complex as you can imagine. You can go something like testing a diode, or all the way to testing a Wi-Fi product where it has a multiple filtering stages and amplification segments. Also, we need to consider a dynamic demand. Serving multiple customers or supporting multiple customers means that each customer has their own design cycle that leaves us with multiple peaks and valleys in our demand. And also, we need to model, I think the most important piece of the puzzle is the human resource. We have people that are barely talented, they are multi-skilled, and they can test different aspects of the products, but also can help us to in other areas as well, not only for testing and assembly as well. So something that we all have access to is Excel, right? So we can just go in Excel and start putting some numbers, add some formulas. And probably that's what most of us we do at the beginning when we're trying to model the capacity of an area. The problem with Excel is it's very limited. And I'm talking about in terms of adding dashboards and being able to compare what-if scenarios. And even if you try to, for example, model or change a production schedule, then it will create a problem with you. Probably you might need to redo 50% of your code. Somebody might argue that you can build dashboards in Excel. Absolutely. The problem is changing the inputs and customizing, with the simulation context is the problem. So that's what one of the reasons why we went to use Simio. Simio is software that comes already with all those tools inbuilt. And one of the most important things for us, as I mentioned, is the experimentation, and that comes out of the box with Simio. Another reason why we went to Simio for this project is we already have a success story with Simio. We went and we modeled the prototype assembly line, and we were able to bring down our lead time from 3 weeks to 1 week per design team requirements. If you can see on your right side hand, and there's an actual screenshot of our dashboard. This dashboard is live, and it's tracking an average lead time of our assembly process. As you can see, it's less than a week. Now, getting back to the model, before we even start modeling anything, we need to set some objectives. And just to mention some of them, obviously we need to have the ability to estimate the capacity based on the different scenarios like demand or the width mix, determine throughput, lead time, cycle time. And again, I don't think I can get tired of reiterating, having the ability to do what-if scenarios. Then I will hand it over to Ryan.
Thank you, Carlos. First, before we get into the simulation software and look at the model, I'm going to just explain the high-level approach that we took with the model in the PowerPoint here. So first, we have jobs arriving either by a schedule or randomly, and those jobs are being represented by an entity. The entities are going to go into what we call a job controlling server, and they have to conduct a particular task sequence that's associated to the job itself. And the first step of that is actually doing all of the test configurations and doing any of the test setups if possible. Once those test setups and configurations have been done, then the job entity triggers the creation of all of the parts that need to be tested as a part of that job. And each part is going to be uniquely going through each of the tests in the test plan. While all the parts go through their test plan, the job order entity is waiting in the job controller server for everything to get completed. And then, so with this, as you can tell, there's not a linear path for the test plan. So each part could take a different path for actually completing all of the tests that are required. So here's just an example of all of the possible tests that we would go to, and we represent these tests as servers, or more so the location where the test could be completed. And there are different locations that could actually complete the different test types. So first, before we even go out to actually completing the test, we're going to determine where that test is going to be completed. So then as, let's just say as part one here starts to go through its test process, it'll enter test one here. And then there's also like for each individual test, as we're starting to test for each part, there's a different a task sequence associated with, the job class, or as, Carlos mentioned earlier, it's more of in the project phases that would dictate what actions are required to actually complete that particular test. So then as, part one completes test one, then it would go to maybe completing test two, but it could have a choice based on these predecessor rules to either choose to go to test two, test three, or test four. But let's just say, for example, part one is going to go from test two to test three, and then to test four, and then finish at report. Now, then after a report for that particular part, we're going to start recording the statistics of how long it took to complete everything. Now let's say part two is coming through now, and after part one finished its test one, part two was able to start, and maybe it's took a different path. So then instead of going to test two because part one was still inside test two, part two started with test three, then came back and completed test two, and then went test four, and then report and completed statistics. And so then once all of the parts have completed all of their testing, the job is then completed, and we start to record the statistics on the lead time and the cycle time of the job and the tests themselves. Now let's do a formal walkthrough through the Simio model that we discussed in the slide. So let's start with first the model structure. So I'm going to zoom in here on the main objects that are really controlling the activity inside the model. So first we have two different sources that are triggering the creation of the jobs. I mentioned in the slide that jobs could arrive either by a schedule or randomly based on inter-arrival time. After the jobs are created, they're sent to this job controlling server that is set up with a pretty simple task sequence to, like I said, set up the test if possible. And then the second part of that is to trigger the creation of each part that belongs into that job. The jobs are then sent to this part test controller. And now this part test controller uses the test order table as a task sequence. So I'm going to now take a break from the objects here and just hop over to the data to explain both the job order table and the test order table and show you what they look like. So coming into the model here, or coming into the data tables of the model here, this first data table for the job order table is each row represents each job, and each job is composed of a quantity of parts for a particular location of a particular class. And so those are really the main attributes of the job that we use. And when using the schedule creation of the job, we use this date requested as the time that we would create the job order. And then obviously this due date is used to set priorities when determining which job to work on next. And then, here at the end of the table, we have some statistics being captured about each of the job as they complete their process through the model. And then similarly, we have a test order table that is associated to each job. So I'm going to actually show this through the relationship here, where if I open up one of these, I can see the test plan that is created for this particular job order. So like I mentioned in the slide, this is a kind of a unique setup for this model in which that every part inside this job order has to complete this entire test sequence. And there's some predecessor rules over here, right, about which jobs need to be done before others, and each part is expected to follow those predecessor rules. So as I mentioned in kind of the slide demonstration, part one would come through and is required to complete this first test first. Then from there, it can complete any of these tests after it's met that first predecessor rule. And then as part two comes through after part one has finished this first test, it will then decide another test to complete based on availability. Once all the parts have completed all of the tests in this report here, which is again what is the task sequence for this particular controller, the part is completed, And the job is waiting for all the parts to be completed. So once all the parts have ran through all of the tests that we just saw in that test order table, it would then also be completed and destroyed by the sink here. Okay, now continuing with the model structure, we have these testing servers down here below that are actually that are used to conduct the test for the actual parts that are coming through. And I'll just point out a couple of unique things about this server. This is a test server, which is a custom object that we are using in this model. And really all of the servers that you see here are the same test server and have the same property configurations, because all of the unique properties of each server are actually being defined from the data tables. So one thing to note is just this processing task is being driven by the master test processing times. And I'll just go to show that table really quickly here. This is the task sequence that would be completed based on the test type that's actually being conducted at that server, the category that that test belongs to, or maybe the job class as it's called in other places. And then the location all dictate, what task sequence that particular test is going to have to follow. And the test sequence is pretty simple. There's like an initial test setup, and then there is the actual test time, which is more like a machine time, and then a change out time to switch over to the new part, or just to take that part out. And again, so all of the test servers are using that table for their task sequence, depending on what type of test type is coming in. And so what's actually happening from this part test controller server is every time that there's a task sequence available to start for one of the parts, it's going to create a copy of itself to go actually complete the testing. And this routing node kind of basically is the gate to get over to your testing, and it makes sure that only one test is being completed for one part at a time. So there may be multiple copies of that part created at one time based on the availability of the task, but this node basically ensures that only one test is being completed for that part. Okay, so now that we've kind of talked about a little bit of the structure here, I'm going to go over a little bit about how this model is used for running different tests. So we have several different model properties set up over here, and I'm just going to kind of cover a lot of them here just to explain how the model will be used. So first, there's these model level configurations where we can set up whether we want the jobs to arrive randomly or by the schedule. Then for each location, which there are 2 locations being modeled here in this model, we're able to set up different resource capacities for each location in the model properties. So the resources include an engineer, and we have 3 different shifts that it could happen, and then also a test tech, which also with 3 possible shifts. And then there's this resource called a temperature chamber, which is required for some of the test types. And those temperature chambers are actually then installed onto the testing servers in reality. So we represent that by seizing this resource so we can model the capacity of how many are available. So after everything runs through that mentioned before in the slide and just in the walkthrough of the objects, we're then capturing these statistics about every job. So there were overall in both from both sites, there were 159 jobs completed over this year that we ran for. And the average lead time, which is the time that the job came in to the time that the job was completed, is reported for every job, and we're able to see an average of that as well here. And then also the job cycle time, which is when we started the job and when we finished the job. So there is, generally due to resource constraints, there is some type of gap of whenever we're actually able to start the job compared to when the job came in. So that's what we're really tracking with the difference between lead and cycle time there. And then we're, tracking how many jobs did we have in progress over that year. And so on average, there were about 9 jobs active for that 1-year run. Then the Skyworks team is interested in having these statistics broken down by these 3 critical job classes that they're looking to measure. So that's really just the same job information that you see here broken down into those 3 job classes. And then we also have some summary statistics about the test and the parts themselves. So, there were over 720 different tests completed. On average, it took, 16 days from a lead time perspective to complete each jobs, but just under 6 days for the cycle time. And really the part information is just more anecdotal there. But yeah, so these are the main KPIs for the Skyworks team that we're using to evaluate the performance of the resource configuration that they have from a setup perspective. So now let's look at some of the results here. So we can actually hop over to the Gantt really quickly too, and just see this is all the activity that is happening. This is that first job that we looked at in the table. And we can see these, all of the actual individual jobs that are being completed. You can tell that there's a lot of parallel activity happening because each individual part, again, is flowing through its sequence of testing individually. So, there's a lot of parallel activity happening for a single job at any given moment. And then, obviously, once all of the test detail have been completed, then the job is just ended, and that's what we see here in this example. One dashboard that has been really meaningful for the Skyworks team here is, let's go to the resource utilization one. This resource utilization is mainly used for the test servers and understanding how busy they are through the runtime. So what we have over here represented with the bars is the total amount of processing time that was conducted on those servers. And then in the line, we see how many tests that were. So we see, for this particular server, there is a high processing time, but also a high test count. Where we can see like some of these like peak, higher in their test counts, but maybe have some lower processing time, so they're less as of a bottleneck, if you will. But the Skyworks team's been able to use this pie chart to really, this bar chart to come up with some different testing scenarios around what benches they should consider or what test servers they should increase the capacity for. And then lastly, as far as some of the results that go into, we've been able to complete a few experiments. And I think, the Skyworks team has probably a bit more of a completed one, but this is one that we were working on together just to show if we're using the random test mode and we're increasing some of the demand that we're experiencing, what kind of impact does that have on the job completion count, which is really the main statistic that they're looking for, but also the job lead time. So the wait time that most of their customers are going to experience before getting that job completed. So, you could say if they have a goal of getting all of their jobs done within this current 3 weeks that is their lead time today, if they were to increase their demand to 125% more, we would see almost of a double lead time to that. So obviously there's going to have to be some resource changes to support a shorter lead time. That's the high level covering of this model, and we're happy to answer any questions once we get to the Q&A. So I'll pass it back to you, Carlos.
Thank you, Ryan. So to touch a little bit on the business impact, if we want to summarize, the impact of the model in what we do is obviously we're going to have a more accurate capacity analysis. But what does that mean for the team and for the business, right? It means that we can put the right resources where they supposed to be, so we can have the most meaningful impact. It also makes us more predictable. You can imagine that having a customer who knows when they're going to get their job orders is very important. And also, as a result, it makes you more reliable, and that makes you more attractive to other customers. For our next project, we would like to take on the product realization process. If you remember my slide where I was talking about the context of where this is happening, the product realization process is a much larger scope than the one that we tackle in this presentation. and it has more meaningful impact for the business if we're able to model something like this. It's obviously more complex, and the reason being is now we're going to start trying to model things like designing, like prototyping, like groups like reliability, production testing. That's something that we're very excited to take on, and Ryan and myself, we're going to start working on that in the next few weeks. Well, thank you for your time. I really appreciate it, and we're more than happy to answer any questions you may have about the model or the process. Thank you.
Hello, Carlos and Ryan. If you guys are ready, ask you guys some questions, and we have a lot of questions from the audience. So, first question: are there any public examples of the job controller server that you used in the model?
I believe there is a Symbit called the parallel route controller that was used as an example for the approach we took.
Yeah. Another question talks about the relationship with Skyworks and Simio. Can you describe the relationship between Skyworks and Simio? How did you get acquainted with Ryan, and how much of the model was built in-house of Skyworks?
So for the how we started the relationship was because I was looking for a system or a tool that it could help me to model the capacity of the lab. But everything started with, as I mentioned on the presentation, with the assembly line. I did that model myself, everything. But then when I got into try to model tests, which is more complex, I had to reach out to Simio, and Simio helped me, redirected me to talk to Ryan. And then basically Ryan took over everything from there. I tried to simulate myself. I got stuck, and Ryan and I, we just decided to start all over. It was something more complex.
Carlos, just another question directed at you. Can you speak more about communicating model results to your stakeholders?
Can you speak? Oh yeah. So well, as you can imagine, I'm talking to VPs and to like directors. So I tried to condense information as much as I could, and I just went straight to the point. In my case, I just went and say, guys, this is the problem. I made a basically stated problem statement, and then I say, in order for us to fix that problem, then we need this many resources in terms of human resources and also in capital, if we want to fix that problem. I just made it 2-3 slide. Typically, I talk to people that have like a 5-minute attention span.
And another question is, how did your organization become aware of Simio?
I got aware of Simio, as I mentioned, I was trying to look for a tool. I started with another tool that I tried before. It didn't fit the purpose. Then I switched to Simio afterwards. I just went and Googled it, basically.
And kind of follow question that too. If you're involved in getting organizational buy-in, how did you get that buy-in from decision makers?
Well, as I mentioned, I put I just called a meeting. I summarize all my all the results, and I just went straight to them and say, guys, if we want to solve this problem, this is how we can solve it, and I have the data to back it up. As I mentioned before, talking to VPs, directors, you have to be very brief and very concise. I also opened the possibility if somebody wanted to dig more into details of how the model works and what kind of assumptions I made. I was more than happy to share all that information with them.
We have a question on experiments. What are some experiments or use cases completed within the model?
Okay, so obviously first I run a baseline. I wanted to know and see if we were very accurate or we were like being able to represent what was happening. And then just after taking a baseline, then I started to move things like people and different shifts. I started to increase what we call a temperature chamber, different resources, right? Like what will happen if I have, instead of 13, 20 of these resources, what will happen if I have another person working on the third shift? And then I went that probably I run, I would say close to 15 scenarios. And then I started to look at my statistics. In my case, I wanted to target what we call phase 2 testing. As you remember in my presentation, there's a phase 2. And I was trying to get a less than 1 week of lead time. So that's what my target was. And I just keep going until I got that below 1 week.
Well, thank you. I want to take this time and thank you, Carlos, especially for presenting it. It's the first of two Simio Syncs in 2022. And thanks as always, Ryan, for your help. I'm sure you're getting a great round of applause for everyone at home. But thanks again.